Thanks, Jeff. Thanks, everyone. It's a pleasure to be here. We welcome the opportunity to be able to speak to everyone about this. It's something that we're very passionate about as a company, and myself personally, and obviously FOSS as our partners in this project, we're also passionate about. So I'm going to spend some time and just go over the hybrid technology that we have deployed here in the port with FOSS, and talk a little bit about our companies and how that technology works, and touch on some of the other technologies that we're working with that are related to that. So our company, Aspin, Kemp Associates, is a Canadian-based company. We work on innovation in the design of power and propulsion systems and other niche type of systems that focus on reliability and mission-critical systems in the marine and offshore industries. We've designed the world's first hybrid tugboat and deployed that along with FOSS, the project that we're talking about here. That's currently working here in the port of LA Long Beach. It's called Carolyn Dorothy. We've done the second hybrid tugboat is also here, called Campbell, and that was a retrofit. So the Carolyn Dorothy was a new build, and the Campbell's a retrofit. So we've pretty much got the bases covered as far as being able to deploy this technology in the hybrid market. We have other technologies like advanced generator protection, which is a system that we patented that allows for much more reliable operation of power plants and mission-critical systems, and reduces emissions. Our technical center of expertise is in Prince Edward Island, which is where I'm based, along with my colleague here, Shaming Lee. This is where we do all our manufacturing, testing, prototyping, training, and deployment to projects that we deliver around the world. Head offices in Stratford, our own Sound, Ontario. We've got offices in Houston and in Singapore, and basically we're working on one in Europe right now. So, FOSS Maritime, from a marine standpoint, got a lot of history. 1889, founded on the West Coast, has global operations with the focus of its operations here on the West Coast. 2 shipyards, one in Seattle, one in Rainier, Oregon. 50 tugs, 70 barges, tugs in the range of 3,000, 8,000 horsepower, headquartered in Seattle. This company knows a lot about tugboats, so it was great to be able to partner up with them on this project. That's the FOSS fleet. The fleet, or the vessel class we're talking about specifically for this hybrid project, was the Dolphin class. There's 3 or 4 of those vessels here in the Port of Long Beach and LA. This technology is applicable to any type of tugboat, or to any marine system for that matter, that has the right sort of duty cycle. Okay, so we are exploring other vessels and platforms that FOSS has that this can be deployed, as well as other owners as well, of course. FOSS has had a very active, aggressive green program. Their environmental stewardship program is pretty impressive. These are all of the things that they've done to date, or it's a list of a few of them anyway. So they are doing some of this diesel oxidation catalyst on Brent FOSS, which is working in the harbor here. Several other areas where they've been certified in environmental programs. Shore power at all the docks that they operate out of. And as a result of those activities, they've received numerous awards over the last several years. Around here, yeah, Port of Long Beach, Los Angeles, Clean Air Action Plan Award. Okay. And so as a result of the work that we did with FOSS, they came to us looking for a technical solution to something they wanted to do and had been wanting to do for quite a while, which is to build a hybrid tugboat. Our company had a hybrid design that we've been considering of deploying on a smaller platform that we were just in the process of going to prototype on. So it was actually a very good fit. That happened probably back in 2006. We went to contract in 2007, and in 2008 we delivered from the shipyard. 2009 it was working in January in the port. So that was kind of the progression that we put the design on the table in our company in about 2002. So that was the progression of the design. And that's the Carolyn Dorothy doing a indirect assist, I think probably the first or second day of work in the Port of Long Beach. with a container vessel. It goes on board that. Hoping everything was going to go right. Duty cycle considerations. So when you talk about hybrid technology, the main thing that you've got to analyze with a marine plant is what is the duty cycle of that plant. That's really where you capitalize on the hybrid technology. So you look at a power plant that has an operating profile that a hybrid plant can work with to improve emissions and efficiency. So we'll go over a little bit of that and how we analyze whether a vessel is suitable or not. So with the tugboat design, the design is focused on the amount of power that the system needs. And often, you'll have a huge amount of power, but it's not used very often. Okay, so they're designed for full-out operation, but typically that's only used 3% of the time. Otherwise, they're at a very low power rating. Okay, so this area where they operate the majority of the time is actually where they're least efficient due to the specific fuel consumption of a diesel engine. It's very high at the lower end of the operating scale, and therefore what we want to do is work a design around that focuses on where the operating profile is most of the time. So you analyze the duty cycle, you find that a typical harbor assist tugboat spends most of its time here. We've got on the y-axis, we've got percentage of time, and here we've got percentage of power on the x-axis. So over 50% of the time, it's sitting at just over 10% power, which is incredible considering the design point is here at 100%. There's another large percent of time that is below 10%, which is when it's just sitting idle and basically looking after hotel load. So what do these bumps represent? And that's part of the duty cycle analysis. This represents just sitting around waiting for the next job. This represents going to the next job. This represents going to the next job a little bit faster. And this represents probably doing some assist work. And then down here at 100%, hardly do that any length of time. So when you see an operating profile like that, you say, wow, this is perfect for hybrid technology. So, said, conventional power plant is designed around this, 100% power, yet it spends all of its time here, or most of its time. And then we overlay that with the specific fuel consumption, or the specific fuel consumption on the same graph. And down here, where it spends most of its time, that's where you're burning the most fuel per unit of energy. So the most kilograms of fuel per kilowatt hour. And therefore, your fuel efficiency goes down. So you might think when you talk about hybrid technology and changing the duty cycle, well, it just takes the same amount of energy to move the boat through the water, so it shouldn't matter whether it's a little or a lot. But it does matter a lot because of this curve. So what we do when we design the power plant for hybrid system is we look at all of these bumps and we design around facilitating or accommodating those areas of operation within the power plant configuration. So we have a configuration that says we're going to operate very efficiently at this power requirement. So at 10 to 15%, we've got a very efficient mode of operation within the hybrid design. So I'll go through a bit of a graphical layout of the system and some schematics to talk about it. But basically here we've got talk about what is a hybrid system. So it's a propulsion plant that uses a combination of energy storage and driveline configuration to reduce or eliminate inefficient operation of diesel engines. Okay? So how do we do that? We use a combination of mechanical, electrical, and electrical power for propulsion. Okay? And we also incorporate some energy storage so that we can switch over to a zero emission mode when the vessel is doing very little, like idle or stopped. And also we have a control system for maximizing all of those modes of operation, and that energy management system is what basically is the brains of the operation. The configuration allows that to optimize the configuration of the vessel. That's just a summary of this propulsion system, which incorporates a combination of driveline configurations, energy management, and/or energy storage to reduce or eliminate inefficient or low efficiency operation of diesel engines.